Hello everyone, welcome back to IPEC by Sounish. So today this is the solution video of the problem that I have uploaded on the Independence Day of India. So those who haven't seen the video yet, they can watch the video, do the problem on their own, and then they can see this solution video. So before moving ahead, I will suggest everybody that whenever you get a hint during the discussion of the problem, you must stop the video and do the problem using the hint again. That's how you can learn better. So let's see the solution. So these are the answers to the two parts of the problem you can see here. So let's see the first problem. So this is the concept part of the problem. Suppose there is a positive charge and a negative charge, then you all know that the field lines will be like this. Now if I take a area here and the flux through this is phi, suppose, and now I made a hole in it, then the flux will obviously change as the surface area change. Suppose the value is phi star, then I can say obviously that phi star will be less than phi because the surface area has decreases. Okay, so uh, I will use this concept here that as I have made holes in it, now the flux will decrease, and you all should know that checkered part means the 50% of the part has holes and the 50% has the material of the flag. So the flux through this whole checkered part will be the 50% of the total area. Okay, because the field lines passing through the holes will not contribute to the flux. Okay, now I will break the problem in three parts. First, I will calculate the flux through this whole area. Then I will remove the flux which doesn't contribute to my answer, uh, and then I will add the flux through this circular part. In these three ways I will calculate the total flux value. So let's see the solution. Method 1. So this is the fundamental method. This is the, you can say, integration method, which all of you have used in your regular courses, I think. So I will take a long thin strip here, and I will integrate it for the whole body. So all of you know that the field lines created by a infinitely long wire are always radially outward. So the field lines through this strip will be like this, and they will also be radially outward from this infinitely long wire. Now if I see this from the upper side, then it will look like this. This is the infinitely long wire, and this is the plane, and this is this strip here, and these are the field lines. Now I have calculated the value of flux d phi through this strip. So I will not discuss how I have calculated, because you all know this calculation. If you don't know, then you can see that here already everything here is written. You can see that and do that problem on your own. Now what will be the value of this angle? What will be the value of this angle? So the value of this angle will be pi by 3, because if you see here carefully that this distance, the distance of the wire from the plane is 9a upon 2 root 3, and if we rationalize it, then you can see that this is 3 root 3a upon 2. Now if we collect it like this, root 3 into 3a upon 2, then you can observe easily that this is an equilateral triangle, whose height is root 3 into the length of the side upon 2. So the angle here will obviously be pi by 3. So if I uh, set the limit of my integral from minus pi by 6 to pi by 6, then I will get this value. Why minus pi by 6? Because I have taken the theta from here, so minus pi by 6 to pi by 6. Okay, so the value of flux through this area is this lambda a upon 3 epsilon naught. Now as I have made hole in this middle part, so the flux value will decrease, and the 50% of the area has holes, so the 50% of the flux will not contribute to my this value. So I will subtract the 50% of the flux through this to get the right answer. So I have subtracted here the 50% of the flux value through this. So you can easily calculate the flux value through this total area, that is lambda a upon 9 epsilon naught. The same method you can replace by a by 3, then you will get the answer that this is lambda a upon 9 epsilon naught, and the 50% of the area has holes, so the 50% of the flux will not contribute to my this value, so I will subtract the 50% of this total value. So I have subtracted here. Now as I have subtracted this, the flux through this circular part has also got subtracted, so I have to add it again because I have subtracted it. So I have to add it again. So what I will do, I will calculate the flux through this circular part. I will take a cylindrical Gaussian surface like this, then I will calculate the flux value. This is phi 1. You can see this is symmetrically placed, so this will be also phi 1, and the value of phi 1, that's mean the flux through this is lambda a upon 3 epsilon naught. But 50% of this circular part has no field, so I will add the 50% of this flux to my total value. I think you are getting my point. The 50% of this has been already removed, so I have to add only the 50% of this flux. Okay, so I have added the 50% of this here, and that's how I got my final answer, which is 4 upon 9 lambda a upon epsilon naught. So this is the final answer. Now this is a very laborious method, so now I will discuss the second method, which is a very good method, and that type of observation is very much needed in exams like JEE Advanced. Okay, so let's see the second method. Now all of you know that uh, if I take a Gaussian surface like this around this infinitely long wire, then the flux through this cylindrical surface will be q inside upon epsilon naught, and q inside is simply linear charge density into the length of the or the height of the cylinder, so that is lambda L upon epsilon naught. So the flux through this cylindrical Gaussian surface is lambda L upon epsilon naught. Now here I will break this problem into two parts, the flux through this plus half of the flux through this. Now we can see that this length, and this length, all of them are 2a upon 3. Now if I remove all the holes from this middle part and make it a solid area, then you can see that this width will decrease and it will be half of the width right now. That's mean half of 2a upon 3. So a upon 3. Then the flag will look like this with a solid part like this, and its total width will be 5a upon 3. 2a upon 3 plus a upon 3 plus 2a upon 3, that's 5a upon 3. Now I will calculate the flux through this, and I will add the flux through this circular part. Now this is the most important observation, that you are able to take a Gaussian surface around this like this. Okay, so I have taken a Gaussian surface around this area like this, and now the flux through this area and the flux through the curved area behind it will be same, because the same number of field lines are penetrating both the surfaces. So the flux through this curved area of the cylinder will be 5 lambda a upon 18 epsilon naught. So this is a very simple calculation. This is a unitary method. So for this 2 pi angle, you know the flux will be lambda into L, length of the cylinder, upon epsilon naught. So in this case, length of the cylinder is 5a upon 3. So 5 lambda a upon 3 epsilon naught. So for theta angle, this will be 5 lambda a upon 3 epsilon naught into theta upon 2 pi. Now in this case, the value of theta is pi by 3. So it will be 5 lambda a upon 18 epsilon naught. So the flux through this part is 5 lambda a upon 18 epsilon naught. Now I will add the flux through this circular part. So the flux through this circular part we have already calculated in the previous method, that is lambda a upon 3 epsilon naught, lambda a upon 3 epsilon naught. So the half of the flux through this will be added to this value, and then we will get our final answer. So this is a very good method and a good observation. So I hope you found today's video helpful and it added some clarity to your physics journey. If you enjoyed this problem, don't forget to hit the like button, share the video with your friends, and subscribe to this channel for more insightful physics problems and solutions. And feel free to drop your thoughts or any questions in the comments below. I'll be sure to get back to you. Take care. See you in the next video. Thank you.